Good morning, Michael, and anyone else who might be watching this video. I'll be talking about my aerospace composite design today. So to quickly reiterate, the project that we were assigned was to design a landing gear for a Blackhawk helicopter. We had a couple of requirements for this assignment. The main ones were that it needs to be a completely composite design. We can have conventional dampeners. It needs to be able to withstand both load cases, and it rests 400 millimeters above the ground. So we had to have some assumptions to simplify the analysis, which were that the helicopter lands perfectly vertical on two wheels simultaneously, so therefore both the forces distributed evenly over each wheel. We're going to ignore tire dampening and cushioning. The mounting points are rigid, and also the cost is neglected considering we don't really have any prices to compare to. So here's a quick brief analysis of the load cases. So we had landing at 1.5 G, added a safety factor of 1.5 for this one as well. We determined this just by using force is equal to mass times acceleration. Using the specifications included, we found that the total force was 0.1457 meganewtons, and after applying the safety factor and then dividing by 2 so that the force is acting on each wheel, it was found that it was about 109,000 newtons. Additionally, there was the crash landing at 40 kilometers per hour. Didn't have much of a safety factor for this one. We determined the forces by work done is equal to change in kinetic energy. It was found that it was 1.273 meganewtons, which is significantly larger, and then after applying the safety factor and the force on each wheel, it was about 636.5 thousand newtons. So I will be designing around, more specifically, the crash landing case so that it just fractures in this, or it just is able to sustain this without fracture. So now we can talk about the design. So I brainstormed a couple ideas in my original concept. The main two I was looking at were flat springs, which are really similar to leaf springs, and disc springs, and both of these work by bending, and I really liked both of these because they're really good for fatigue resistance. I found that disc springs, you needed a lot of discs in order to get more deflection. So I had come up with this design where I combined both of them. However, I found that this was a little bit difficult to manufacture, as you can see here, and there would also be a little bit of torsion, so there'd be a bit of stress concentrations in the flat springs. But I did simulate it anyway just to have a look at how it would be, also for a bit of fun. So my final design was a little bit more simplified. I just decided to go with disc springs with a dampener at the end of the shaft, and disc springs fixated to the shaft. So you can see how this would look during a typical landing. As you can see, the wheel will hit the ground and the springs will compress, absorbing some of the energy. So for material selection, I chose carbon fiber pre-preg woven fabric. So I chose the lower modulus one pretty much because it's got more compliance, so it allows for a softer landing, and I found through running simulations that there was less stress. So with the woven fabric, I decided to make a quasi-isotropic material by having one weave at 0 degrees and another weave placed on top at 45 degrees, and these would alternate in the laminate. So the analysis, I used shell elements. I initially was using solid elements, but I found it was very computationally expensive. So I decided to use shell elements, and this would allow me to use the ACP tool, which has far more accurate material analysis. so I could assign laminates and analyze each individual ply. So as you can see here, my first design did not work very well. It had a high failure, about 8,000 megapascals, which is far too high, and this isn't actually even using the layer by layer analysis. But it did deflect 352 millimeters, so assuming it didn't fail, the bottom of the helicopter still wouldn't touch the ground. So we can see here that analyzing it in ply by ply, we can see the stress concentrated regions in each laminate. So the stress is here, and this also shows you that using just a typical shell element is not as accurate as using the ACP post-processing tool, so because the stress values are quite different. Now we can also see here that we can analyze regions of failure. So I've looked into previous study, and this is typically how a disc spring will crack. It will crack along an edge like this. Here we can see that the spring will definitely fail in the load case. So I overcame this by increasing the thickness significantly. As you can see, this drastically reduces the stress down. So there's far more laminates now. There's about so much that it makes the ply thickness to be about 10 millimeters. And it deforms much less. So unfortunately at this point it still does fail. However, I realized that basically the best solution wouldn't be to just keep increasing the thickness, and to instead I have a couple options of increasing the number of disc springs in series, having springs in parallel, although this will also increase the stiffness, or changing the angle that the springs are manufactured. So the most optimal design couldn't be determined because I would have to do a lot of parametrization. But you can still see that increasing the thickness does significantly reduce the amount of failure present. So now we'll talk about the manufacturing process. So for manufacturing the carbon fiber, I chose to go with the pan process. That's because of its superior mechanical properties and quality. So it has much higher tensile strength, but also has a lower stiffness, which, as we know, tensile strength and modulus are inversely proportional to each other for carbon fiber. But this is a good thing anyway, because as we established before, a lower stiffness will allow a little bit more deflection, so a softer landing. And it's just got a high strain to failure, so it's less likely to fail. In the pan process, polyacrylonitrile is first stretched, it's melt spun as well, which is what causes the high molecular orientation. After that, it's heat set, which is the cross-linking process. Operates at about 200 to 400 degrees. It's carbonized and graphitized, so both of these processes drastically increase the carbon content to 95, 99% through dehydrogenation and cross-linking, more cross-linking. After that, we've got surface treatment, in particular sizing, epoxy sizing. So what this does is it adds a protective coating to the fiber, which will prevent cracking, but it also promotes a bonding interface with the matrix. And after that, it's wound into a spool. What we'll be doing is we'll be weaving it. So we'll be weaving it into a 2x2 twill, which is one of the more common types. And we're also doing this because it's got less crimp than other fabrics, excluding satin fabric. It has better draping ability than basket and plain weaves too. So it's then pre-preg. I chose to do pre-preg because of the excellent properties. It's very controllable as well. Pre-preg is basically where the woven carbon fibers are pre-impregnated with epoxy that's in B stage, so the curing process has already begun. It's worth noting that we should handle the material with gloves. We do this to prevent contamination with oils from the skin and also to minimize epoxy reactivity. So after that, the discs are formed via cold compression molding. So basically the pre-preg is laid into the mold slowly compresses, it forms a net shape. This is good because it's got very low shear forces, therefore the fiber lengths are all the same length. It's pre-preg, so it doesn't need to be required, and this is important because it allows for rapid processing, since pre-preg you want to have the material built as fast as possible. Thank you very much for listening.